Alrighty, y'all. Today we're taking a look at question 4 on recitation number 1. And for this one, we're trying to figure out the fraction of total electrons that we have to move from the penny to the plate in order to lift up the penny. So we have a penny with a given mass. Some distance away, we have some plate. And we're going to be moving electrons one at a time until we can lift up the penny. And we have how many electrons per copper atom, and we also have the mass of a copper atom. So when I'm thinking about the fraction moved, the fraction of electrons that need to be moved, in order to get that fraction, I have to know the number of electrons that I'm moving, and I also need to know the number of electrons that I have to begin with. So it's going to be like a two-stage problem for this one. Let's look at the total number of electrons first. So I like to do this one kind of thinking in terms of dimensional analysis. So if I have this much mass per penny, right? So I'm trying to figure out, I'm trying to end up with number of electrons per penny. All right, for every one penny, how many electrons do I have? That's going to be my ending dimensions for my number total. So if I start with that it's 3.11 grams for a 1 penny, right? So for every 1 penny that I have, it's 3.11 grams. But also, for every 1.055 times 10 to the negative 22 grams, it's 1 copper atom. So I want to be canceling out grams, so I'm going to put grams in the denominator, 1.055, 10 to the negative 22 grams for every 1 copper atom. So grams cancels, and now I know the number of copper atoms in a penny. Well, I don't want the number of copper atoms in a penny, I want the number of electrons in a penny, so we got to keep going. I want to get rid of these copper atoms, and I know how many electrons per copper atom. So I can say, okay, for every 1 copper atom, there's 29 electrons. So copper atoms canceled out, and I'm left with electrons per penny. If I multiply this all the way across, I'm going to get 8.5488 times 10 to the 23 electrons per penny. So that's step 1, done. Now we need to figure out how many copper atoms we need to move in order to lift the penny. And this is probably the trickier part. This is the part that requires our electromagnetism knowledge, our Coulomb's law. So let's think about what that's going to look like. Well, in order to lift the penny, in order to lift anything, I need some force to overcome the force of gravity. So if I'm thinking about how many electrons I need in order to just barely be able to lift the penny, then I'm going to say that my force, my electric force, and my force of gravity, right, that has to equal 0. It's not accelerating, but it's about to be accelerating upwards. Any more than this, if this was any greater, then it would be some positive acceleration. So if I rearrange this, Fe equals negative Fg. Notice that I'm keeping my vector notation because I haven't thought about what direction either of them are going, but I just know if the thing is in equilibrium, then it's about to be lifted up. So what I'm going to do is I'm going to think about, now that I've set that up, now I'm going to think about the directions, sorry. So I know that gravity is going to be pulling down on the penny, and I know that the electric force has to be lifting it up. Let's call that there. So if I were to turn this equation over here into magnitudes and directions, I would say my magnitude of my electric force, that's going to be going in the positive J direction. And gravity, I have my magnitude of the gravitational force and that'll be going down, so it'll be in the negative j hat direction. And just opening up, these two minus signs will cancel with each other. I'll have FE j hat equals FG j hat, and the j hat on both sides can cancel as well, which ends up giving us that the magnitudes of those two forces will be equal, which we probably could have gotten intuitively from the very beginning. I just wanted to show a little bit more vector work of working with these j hat notations. So this tells me my magnitudes of my forces are equal, which makes things easier because I know how to describe an electric force and I know how to describe the force due to gravity. Force due to gravity, well, that's just going to be my mg in this case. And my electric force, again, since we're just thinking about magnitudes, it doesn't matter any positive, negative. I just have to think about Q1 and Q2. How big are those charges? And I can set them equal. So, how big are those charges? Well, every time I take one electron off of the penny and put it onto the plate, the charge on the plate will get more negative by the amount of the charge of one electron. And the penny will get more positive by the charge of one electron. So however many electrons this one loses, this will gain, which means that they will have the same charge just with opposite signs. So if they have the same charge, opposite signs, well, I already said I didn't really care about the signs because we're talking magnitudes. So if they have the same charge, I'm just going to call that charge Q. So it'll be K times Q, will be Q times Q, so it'll be Q squared over R squared equals mg. So just to talk about what we do and don't know on this, we set all of this up talking about forces, but I don't know what I'm trying to use this to solve for. Well, I know what G is, that's a constant. I know what K is, that's a constant. R, the distance between the objects, that was given in the problem, so I know that. I was also given the mass of the penny, so I have to be solving for Q. Which makes sense, because if I can figure out how much charge I need to put on the penny in order to get it to move, well, that will help me figure out the number of electrons that I need to remove from the penny in order to get it to move. So, rearranging this, and I'm solving for Q. I'm going to say that Q is going to be the square root of R squared mg over K. And something to remember as we're plugging in numbers is that we want everything in base units before we plug it in, because otherwise we have to worry about units, and I don't like worrying about units. So 5 centimeters, that'll be 0.05 meters, and 3.11 grams is 3.11 times 10 to the negative 3 kilograms. So if I come over here, that's what I'm going to be plugging in. It's my radius, 0.05 meters. My mass, 3.11 times 10 to the negative 3. G, that's 9.8 meters per second squared. I have not been writing units for anything else. Don't know why I wrote it for that. K, that'll be 8.99 times 10 to the 9th. Or 9 times 10 to the 9th if you want. We all know I don't love rounding. That's just for me, but 9 is perfectly acceptable to use for that. So, solving for that, the charge required to lift up the penny is going to be 9.2946 times 10 to the negative 8 coulombs. Beautiful. So we're almost there. I know the charge that I have to move in order to lift the penny. And now I need to figure out how to use that to figure out the number of electrons I have to move. Well, let's say I had to move a charge of 4 coulombs, and I knew that for every 1 electron was 1 coulomb, just for example. I know in order to move 4 coulombs, I would have to move 4 electrons. So that's all we're going to need to think about is the total charge that I need to move. If I can divide that by the number of electrons, if I can take the total charge that I have to move and divide by the charge of an electron, that will give me the number of electrons I have to move. We can kind of show that with dimensional analysis as well. So I have 9.295 times 10 to the negative 8 coulombs that I need to be moved, that I need to move. And I want to get rid of coulombs and make it number of electrons. Well, for every 1 electron, I know that it's 1.602 times 10 to the negative 19 coulombs. So my coulombs will cancel and I'll be left with my number of electrons. So this will come out to be 5.80185 times 10 to the 11 electrons. So now we have the total number of electrons in a penny and the total number of electrons that I need to move in order to lift the penny. So in order to get that fraction, my fraction of the total will be my number of electrons that I need to move divided by the total number of electrons that I started with. And punching that into a calculator gives us 6.7867 times 10 to the negative 13. And it's unitless because it's just a ratio, it's just a fraction. All right. Well, I hope you found this video at least a little bit helpful. Let me know if you have any questions about this or anything else that you want me to try to explain, and I will do my best to try to explain it, because I guess Sydney explains stuff.